Today I would like to explain the principle of operation of solar panels, and more specifically, the photovoltaic cells they are made of. Those cells are made of semiconductor materials, most often silicon. If you know how a diode works, most of what I say will be familiar to you, because a photovoltaic cell is essentially a modified diode. The silicon atom has 4 electrons in its last shell. Quantum physics says that only the electrons in the last or outermost shell are involved in the bonds between atoms, and that the atom strives to have an octet or 8 electrons in this shell. To make 4 electrons to 8, an atom is linked to 4 other atoms in such a way that each electron in the last shell of the first atom is linked to 1 electron of another atom. Each subsequent atom is complemented by the next one, etc., so that each one has 4 neighbors, except those at the edge of the silicon body. In this way, a regular lattice of atoms or crystal is formed. For the sake of simplicity, I'm going to present it in 2 dimensions this way. A photovoltaic cell is made not of pure silicon, but of 2 layers intermixed with other atoms, characterized by different number of electrons in the last shell. Adding such atoms to a semiconductor is called doping, and the added substance is a dopant. This is a dopant with 5 electrons, for example phosphorus. The vast majority of atoms in the crystal are still silicon, which dictates the crystal structure, in which each atom connects with 4 adjacent ones. Therefore, in the last shell of the dopant atom, we have 5 of our own electrons and 4 of others, so a total of 9 and not 8. Therefore, 1 electron is not attached to the nucleus and can move through the entire material, so it can conduct electricity. So far I haven't explained where the electricity would come from, but I will get to that later. And now for a change, a dopant that has 3 electrons in the last shell, for example boron. An atom has 3 plus 4 equals 7 electrons, and it tends to have 8. It is willing to fill this hole by attracting an electron from the neighboring atom, and then a hole is made in the neighboring one. The hole is nothing but a missing electron in the last shell. As a result of electrons jumping, the holes move as if they are particles. Here we see a hole traveling to the right. Since the hole is the lack of an electron, it acts as if it has a positive charge and can take part in conducting the electricity. I will call electrons and holes charge carriers. The first dopant presented here at the right-hand side is defined as the N-type for negative, because it contains negative charge carriers. The second is P for positive. In addition to the described phenomena, the atoms are in constant vibration due to the fact that the temperature is above absolute zero. As a result of these vibrations, it happens that an electron spontaneously breaks free from an atomic bond, and then this electron becomes a free electron and thus a charge carrier. In the place where it initially was, a hole is created, which is also a carrier. This happens both in the p and n-doped material. As a result, the n-type material has not only electrons, but also a small number of holes, and the p-type material has a small number of free electrons. They are referred to as majority and minority carriers. Majority are those with the majority in a particular layer, that is, in the n layer electrons are majority carriers, and in the p layer holes. Minority are the other ones. There are really few minority ones, on the order of 10 to the minus 10th of the majority, but later we will see a situation in which more of them can arrive. In a solar cell we have a p-n junction, that is, a silicon crystal doped with p-type in one area and n-type in the remaining area, so that these p and n areas touch each other. Let's look at the behavior of this junction, assuming for now that no light is falling on it. At the junction of the p and n regions, there is a sharp change in the concentration of holes and electrons. This causes diffusion, That is, the electrons flow from the n area, where there are a lot of them, to the p area, and holes travel from the p area to the n. So both types of majority carriers shift into areas where they are considered minority. Remember that a hole is nothing but a missing electron. If an electron appears in the p part, it can fall into such a hole and plug it. And then neither a hole nor an electron remain. We call it recombination. It will also take place in the opposite case, when a hole falls into an area where electrons are in the majority. As a result of majority carriers escaping to the other side of the junction and of recombination, a depletion layer is formed in which these carriers are missing. Until now, the diffusion has seemed to blur the differences between the n and p regions, but let's not forget that atoms have a nucleus that has as many protons as the atom has electrons. If the electron flows out of the atom, the negative charge of the remaining electrons will be too small to balance the charge of the nucleus. A positive ion will be formed. Similarly, negative ions are formed when extra electrons have flowed in to fill the holes. Diffusion compensates for the carrier concentration difference, but creates a charge difference. These charges create an electric field that acts on the electrons and holes, pushing them in the opposite direction to the diffusion. As a result, the carriers diffuse slower and slower. The electric field also affects minority carriers as much as it does on majorities. Minority carriers in the depletion zone drift to the areas where they will become majority. In summary, each carrier travels from the p or n region where they are now to the other region. As a result, minority carriers become majority carriers, and majority ones become minority ones. And with each such change, they change the direction of motion until they recombine. It will never happen that all carriers will recombine and the process will cease, because new electron-hole pairs will continue to be formed as a result of the thermal vibrations discussed earlier. The depletion zone will expand until it creates an electric field so strong that the drift of minority carriers will counterbalance the diffusion of majority ones. Now we shed some light on the junction. Light is a beam of photons. An electron in an atom can absorb a photon and use its energy to break free from the atom nucleus. A hole is created at the site of the electron. What we have here is the generation of an electron-hole pair, just like in the case of thermal vibrations, but while that process took place rarely, this one can occur on a significant scale. Let's assume it happened in the n-type region. The newly generated carriers will behave the same as the others existing in the n region, that is, the electron as the majority carrier will diffuse towards the p layer, and the minority hole will also drift towards the p layer. At first glance, the negative charge flies to the left, the positive charge also flies to the left, so in total no charge moves. But the situation where the drift offset the diffusion was there before illuminating the junction. It was when there were many electrons in the n region and few holes. In order for the movement of a small number of holes to balance the movement of a large number of electrons, the drift velocity of a single hole must be greater than that of a single electron. If so, the hole in the new pair will travel faster than the electron. If this is repeated many times for different atoms, there will be excess holes in the p layer. Similarly, we can follow the case when light hits the p layer and then excess electrons are created in the n layer. Now, assuming our piece of silicon is connected to an outer circuit, the increased amount of electrons in the n region will force them out into the wire. They will continue to flow through the circuit and will eventually fall into the p area. We have an excess of holes in this area, so the incoming electrons will recombine with the holes. This way, both excess holes and electrons will be cleared away. The process will repeat for each electron-hole pair generated by the incident light, so there will be a continuous flow of current in the circuit.